It is with my great pleasure to introduce Mr. ISRU. And folks who actually have been working with ISRU, for those folks, Jerry doesn't need an introduction. Originally, he started as a propulsion engineer at Johnson Space Center. And soon he realized to make a journey to Mars and back feasible, you need to mine your own resources and refuel the empty tanks. And since then, for the 20 years, he's been putting all the pieces of the technology together to make it happen. Personally, to me, the sort of one of his first eureka moment was back in 2010 on the slopes of Mauna Kea in Hawaii, where Jerry put together entire system, end to end. We called it from dust to thrust. So there was a machine that would mine regolith, machine that would extract water, machine that would electrolyze it, and then eventually a rocket thruster. And conveniently, you guys waited till everyone was gone to have so much fun and fire this rocket, because I haven't seen it. The Mars 2020 has an instrument called MOXIE, and in large thanks to Jerry. Jerry has been really pushing very, very hard within NASA headquarters to make ISRU a demonstration on the next Mars mission. So that's why MOXIE is flying. Currently, Jerry is no longer at Johnson, he is at NASA headquarters. He's a sort of lead of the ISRU system capability team, and potentially you're gonna talk about it, maybe some of this.
A little bit, yeah.
Doing. So with this, thank you very much.
Thank you. Well, I definitely want to start by thanking Vlada and Michelle for inviting me here and making it possible for me to attend. I also want to thank the previous speakers because you've covered different aspects of what I'm going to be talking about, so hopefully I'll get through my charts even quicker. I'm going to be taking a slightly different perspective than the other speakers. And in particular, Vlada had asked me to try to cover some of these topics. I always start out with what is ISRU from our perspective and why do we actually want to consider it in missions. Do want to talk a little bit about the resources and their locations of interest that were discussed. Some of the challenges and risks for ISRU. How do we, what are the things that we have to overcome to enable missions and to convince people to use it? Some concepts of operation, in particular for water-based ISRU on Mars, and then a little bit of discussion at the end, hopefully, about water-based ISRU and whatever connections there might be for both planetary protection and search for life. My presentation is specifically aimed at being a chart package for folks to look at afterwards and not necessarily have to listen to me and still actually get useful information. So you'll see them fairly crammed with information. Hopefully I won't spend too much time on those. So to begin with, I always like to set the stage for what is ISRU. Very, very top level, it involves any hardware and operations that harness and utilize in situ resources to provide a product or a service. And in situ is interesting because it covers a wide range of things. It's the normal things we think about, the Mars atmosphere, water and such, but it does cover other aspects. Trash, discarded materials, spent landers. Those are all resources that should be considered as well as the environmental conditions might be a resource. Our unofficial logo for ISRU is a vulture flying over the moon or a planetary surface holding a pickaxe and a garbage can, because anything is a resource. We typically look at the top three. What are the resources? Do we understand them well enough? How do I acquire those resources? And Chris gave a fantastic presentation on some of the methods on how we would do that. How do we then process those resources into a product for potential immediate use? Oxygen, fuels, things like that. Or how does it create feedstock for some of the other things we might want to do? Manufacture parts, construct things, or generate and store energy. It's very important to recognize that ISRU requires a customer. By definition, it's providing a product. So if the other systems aren't designed around to accept ISRU or to understand those, you've basically lost a lot of your benefits. So we'll talk about these top 3 ones pretty much as the primary focus of the KISS study. There are lots of benefits for why you might want to include ISRU. The 2 top ones are basically reducing launch mass, and in particular for Mars, either increasing the payload to orbit through a better delta V or higher rendezvous orbit. However, when you add water to the mix as a possible resource, the number of potential benefits or solutions to architectures increase drastically. It opens up possibilities for reusing hardware like landers and hoppers. It opens up possibilities for larger scale surface power systems based on fuel cells, backup to life support, different food processing ideas. And that comes from the fact of, we look at what's called the gear ratio, that for every kilogram of material, whatever it may be, that you land on the Moon or Mars, that requires, propulsive stages and propellants to get there. And if you work your way backwards, something on the order of 7.5 to a little over 11 kilograms of material has to be thrown into Earth orbit just to land any 1 kilogram of something. So if I'm making 20,000, or 20 metric tons of oxygen or 30 metric tons of Ascent propellant to get off Mars, and I multiply that by 7.5 or 11, you're basically talking about saving something on the order of over 300 metric tons of material that has to be launched into the Earth's orbit. That means something on the order of 3 to 4 SLS launches. So significant mass savings can occur when you start thinking about making things, at your destination versus bringing everything from Earth. The 2 key things that we have to deal with whenever you talk about ISRU and making a product is how much product do you need to make and how much time do you have to make it. That sizes your system, your excavation devices, the power systems you need, and so the infrastructure to make that product, in comparison to what it would take for you to bring that in the first place. So there has to be an economics associated with, why do I want to send that hardware someplace versus just bring dumb propellants in the first place. Part of that is that gear ratio discussion. Now, with respect to NASA, it has a fairly focused and limited perspective on ISRU, typically at the beginning because of uncertainty. So the green box basically shows that, for a human Mars mission, we're currently thinking about just the Ascent propellant, maybe just the oxygen, maybe the oxygen and fuel. However, we do need to consider horizon goals. If we're going to the Mars over and over again, maybe not making a colony yet, but if we're going there, what are some of the other things that we might do and prepare for so that we don't make a decision that would send us down the wrong pathway? So some of the things, I put together charts on different studies over the years and how much consumables they've thought about needing and how much time they've provided for those. 2 studies in particular, one by Langley on a reusable transportation system on Mars, and another one for Mars water-rich study, kind of show maybe where we might want to go with respect to using water resources in ISRU for consumables versus just the first kind of missions that we send humans there. A study, Julie Kleinhens from NASA Glenn is here. She led a study with Aaron Paz at the Johnson Space Center on looking at an early Mars mission, human mission, through the Evolvable Mars campaign, and considered several options: the non-ISRU, bring everything, just making oxygen and fuel, and then adding more for life support with respect to the Mars water-rich study. And they went through and they sized the hardware and the power systems and such, and they came up with some very interesting information. To begin with, if you're bringing everything with you, the propellants, versus if I just make oxygen, I'm on the order of saving about 73% of the launch mass, versus if I make oxygen and fuel with water resources and atmospheric resources, it drops it down to 94% compared to having to bring that propellant from Earth. Interestingly enough, the size of the hardware plays into that as well. So if I'm just making oxygen, I need about a little less than a metric ton of hardware. However, I'm bringing 7 metric tons of methane with me. So the Earth mass that gets sent to Mars is on the order of 8 metric tons. I'm making 30 metric tons. So it has kind of a ratio of close to 3 to 1. However, if I'm going to mine water, I need an extra metric ton of hardware, but I'm not now delivering the 7 metric tons of methane. So bringing 1.7 metric tons of hardware now changes that kind of gear ratio of goodness. And then looking at other masses, you have to increase your water mining capability. The interesting thing, though, is when you start looking at, we did not look at ice in this study. We looked at the kind of granular material that may be found most places on Mars that has a low weight % water. And we looked at potentially hydrated materials that may exist in some of the equatorial sites on the order of about 8.6 weight %. And what we found was, from a power perspective, if you're even at the 8.6% by water mass, you're very similar to just making the oxygen alone, but you're getting all that extra mass savings. So it says even a low weight % water content provides significant benefits. So from that perspective of why ISRU, why water resources, the conclusions for Mars should be, hey, water is pretty abundant on Mars. I think we've heard a little bit about that, especially from the ice perspective, and I'll talk about it in the next section. Water resources provide significant benefits for human exploration that can't be considered, or should be considered, and that even at low water concentrations, you can provide significant benefits to the mission. So now quickly into the available resources. One thing that we do for ISRU, and especially since I've gone back and forth between are we going to Mars, are we going to the moon, are we going to Mars, now we may be going to the moon again. Throw in asteroids somewhere in that mix. We try to look at, well, what are the resources that we're really interested in, and what are the benefits, and can we find them at multiple destinations? And water is one of them that, talking with Chris during the last break, 10 years ago, we really didn't think about water too much on the moon or Mars, and that has changed drastically at both of those locations. And there are things that we need to take advantage of for that perspective. For Mars itself, the resource of primary interest that we've thought about for the 20 years that I've been involved in ISRU has been the atmosphere. Carbon dioxide can be found anywhere. Over 95% of the atmosphere is carbon dioxide, with some really nice traces of nitrogen and argon that could be used for other things. However, we have started to spend a lot more time looking at the water. As I mentioned, we are spending a lot of time with respect to just the low weight % soils, as well as hydrated minerals. But a lot more emphasis is now being spent on the ice that may be present as well. By no means am I a Mars scientist. I steal a lot of charts, or quote, borrow a lot of charts from other folks that do the really good work, and I kind of combine them here to show that here again, water seems to be very prevalent at different concentrations all across Mars in different forms, and whether they're aqueous minerals or subsurface ice sheets that may be visible due to craters and such, or the polar ice caps. All of those are very interesting forms of water that we try to consider from an ISRU perspective. This was a little bit more information about what we know currently about the hydrated minerals. I won't go into that. I think some discussions have already been given on the glacial features that exist and that could be taken advantage of. This chart in particular was talked about by Thane, and so I'm really glad that we talked about the different potential polar ice, and I had to throw in a Gerald data chart here, even though I can't explain it. It's good background information. In general, now going to the landing sites, it's very interesting. Back in 2015, the Science Mission Directorate and the Human Exploration Program put together a workshop through the Lunar and Planetary Institute. They opened up a call for teams to be formed to propose landing sites on Mars that dealt with both science and resource aspects. 47 exploration zones, or EZs, were proposed through 45 different abstracts. They looked at a wide range of different elevations and different latitudes, some bearing hydrated minerals, some bearing ice deposits. A little bit more in the equatorial hydrated mineral case, but a significant number that dealt with subsurface ice. But it brings up some very interesting points about landing site selection. Before you think about science or even resources, you have to step back from a mission perspective and look at it from a practicality point of view. And the first drivers are altitude and latitude. Those have major impacts on your landing system, on what type of sunlight you might expect at that location, what the daily and yearly temperatures are like, what the atmospheric pressure is at that location and how it influences ISRU, for example, and the potential for dust storms that may occur. From a local perspective, so once you kind of figure out maybe a region that you're interested in, you then have to get down to the local region. Looking at landing, what's the terrain like from a landing perspective or an infrastructure perspective or a mobility perspective? Once you've kind of found, weeded out the bad places and you have reasonably good ones, then you can start diving into, well, what are the scientific merits associated with those? What's the search for life? What are the available resources? And it's pretty much a cyclic situation, because you have to have that in mind to begin with to look for landing sites, but then you have to kind of weed out potential landing sites based on those other aspects. For example, if I don't have a nuclear reactor, that may limit me to certain regions or latitudes on Mars that may be considered realistic. This chart is one that I threw up just to kind of educate a little people on the impact of latitude. So for example, just like on Earth, as you move up in latitude from launch sites, the amount of payload you can launch into orbit is decreased because of the Coriolis, spinning of the Earth and such. So how does that translate to a Mars lander, an Ascent vehicle? And so here was a case where they looked at a typical Mars lander, and it's kind of designed at that time for a maximum of about 30 degrees latitude on Mars. And and then they extrapolated it to look at, well, if we tried to go up to 50 degrees, what would the impact be, for going for a location where ice might be, and to open up that landing site selection process. And so I picked, basically looking at Jezero Crater, which is about 18 degrees. It's one of the Mars 2020 landing sites of interest. It has potentially hydrated minerals of interest for ISRU, versus say 40 or 50 degrees north latitude in terms of where the ice sheets might start or where you might be in. And you see basically about an 800 to 1,500 kilogram delta between those two missions. Well, again, using that gear ratio aspect, that means that my payload to Mars or to Earth orbit has increased as a minimum of 6 metric tons to potentially 16.5 metric tons. So it has an impact on where you might land and the implications on your landing systems and such that can't be ignored. So what are the challenges and risks for ISRU? We've broken them down into 4 major categories. The first one is the resource. What are the risks associated with it? Do we know enough about the material and where it's located and as such? There are technical challenges. Can I really do this? Can I really excavate and process the hardware? Chris brought up the TRL aspect. Is the technology ready to do this? Have I demonstrated it? Can I do this for long periods of time without a crew being there? Can I do this without maintenance and high reliability? There are operating challenges. Depending on where I land on Mars or the Moon, there's different environmental aspects, different temperature ranges, different dust ranges, the lower gravity aspect of Mars or the Moon or asteroids. All those are challenges that we have to take into consideration. And then lastly, how do I integrate ISRU into the other systems? Are the propulsion systems, the life support systems, the power systems willing to have those products? Is the ISRU product of the right quality and quantity, things like that. And so we look at those challenges and risks, and where would you buy down those risks most likely? And there are some that, you know, there's a lot we can do on Earth. Chris brought up analog sites and test chambers. Those we will use extensively. But in the area of resources, in the areas of how do I operate in these environments, those are things you pretty much have to do in situ. You can get a good guess doing them on Earth, but until the rubber hits the road at that place, there's always going to be some level of risk that you may not be willing to take if it means life or death for an astronaut. So, working with others, you look at, well, how do we buy down the risks for the resources? You start, as Chris was showing, you start from the orbital aspect, and you go down to the very fine details on surface, the ground truthing. And we see that we have a pretty good knowledge, and we're gaining a lot of knowledge from the global perspective. But as we get more and more to finer details to what we want to do with that resource and what risks may exist, there still is quite a bit that needs to be done. When you look at it from a terrestrial perspective, they kind of go through a cycle where you pick your site that you're interested in, you send, based on orbital data, maybe some limited telemetry or aerial imagery. You send a geologist or someone out to that site, they do a precursory assessment. They either give it the thumbs up or thumbs down. If they give it the thumbs down, you have to go back to the first step of picking a site. If they kind of give it a thumbs up, you go there and you look at it more focused. You do a more detailed ore body assessment. Here again, at some point, you have to make an economic decision as to whether that's a good site or you abandon it. If it's a good site, you go to the next step. How do demonstrate the extraction concept? This typically can take years, on the order of a decade or more on Earth, and billions of dollars are spent doing this. So how do we condense this to some extent for human missions to the Moon and Mars is a very big question going on. So I'm going to quickly go into concepts of operations. Here again, the baseline is atmospheric processing. It's everywhere. The chemical processes are pretty standard in some cases. Life support systems use a lot of the same technologies. So it's considered a reasonably low risk approach. When we start looking at different water resources, there are pros and cons associated each one of those in terms of the concentration or how easy it is to extract it. There are site specificity aspects associated with them, especially as you start going towards the icy subsurfaces. There are different excavation or extraction techniques. We broadly break them down into in situ versus reactor type of assessments. So in situ is you're trying to remove the water from the location at which it's found. There's been, I could drill a hole and beam energy into it through microwaves or solar energy. I could stick a thermal probe down there and heat up and cause the water vapor to, the ice to basically sublime and turn into a vapor and collect it. The Rodriguez well concept is the far right, where I've now drilled into an ice sheet. I've added enough heat to basically create a liquid pool, and then I extract liquid from the subsurface. Those are all in situ methods. An interesting thing to note is even though from the water vapor curve diagram, it seems that water might be stable on Mars. It really isn't. A colleague of mine, Paul Niles at JSC, pointed out that you really have to look at the vapor pressure of water, not the pressure, atmospheric pressure itself. So when you look at the vapor pressure of water, it's significantly below the stable region. So that's why you basically go from ice to water vapor and skip the whole liquid phase. Now, I can contain the material in one form or another, and I was really surprised. I have actually more information, I think, from Chris than Chris showed in terms of, but basically Honeybee has looked at several concepts associated with how do I kind of capture material, hold it in some kind of a vessel and heat it up there versus necessarily in situ per se. Chris brought up the idea of augering material up to the surface and dumping it into a reactor if it's hard material, or just scooping it up and throwing it in if it's low weight percent. And you could do that on a rover or have something deliver it to a stationary unit. One very quick thing to think about is a lot of decisions have to be made to eventually select your ISRU system. There is a trade of a number of different decisions you need to make. Each one of them will influence how you perform ISRU. So atmospheric only, follows a very direct path, whereas if I'm going for different water sources and when I incorporate that into missions can make you fall in different pathways. The power source is a very important one that needs to be considered. Another thing that we look at from ISRU is when are we going to implement it and what's the growth? The Evolvable Mars campaign was really great in the fact that they decided we were going to go back to the same location several times, and how would you build up the infrastructure and how would that change how you explored? And with respect to ISRU, that may cause us to think about, well, what are the easy resources that I could get to first? And then what are maybe some of the better resources that I could get to as time goes on? That might be a decision point between, say, a hydrated mineral and subsurface ice. Do we go straight for subsurface ice, or do we do something simple to begin with? Those are debates that we should have. It also has an impact on how we might mine water. So for example, do I mine the material and bring it back to my Ascent vehicle and ISRU plant on my early emissions? Do I mine the material over here and bring back dirty water to my processing plant in my early missions? And eventually I'll probably want to have distributed ISRU systems with depots and such that just feed to multiple customers. This chart is basically now starting to make us think about going from the theoretical approaches for extracting those resources to what have we done. With respect to hydrated and granular material, we've actually done quite a bit in terms of designing and testing implements for excavation and pneumatic transfer of materials. We've done quite a bit in terms of how do I heat up the soil and drive off volatiles that could be captured. In 2008, we tested two what are called hydrogen reduction reactors for the moon, which basically take granular material, heat them up with hydrogen, and makes water. That same technique could be used on Mars, and we're currently looking at two concepts. One is an open heater that uses the Martian atmosphere to blow what's the water heated off or driven off versus an auger. Pioneer Astronautics has spent time on the idea of sending hot CO2 through a bed of hydrated materials, capturing the water and condensing it. So things have been done that point to that we can do these things at some scale. Now it's a matter of engineering how much energy and mass is associated with it. And here's just a very simple pictorial of all the steps that might need to go into this from a concept of operations that we now are starting to talk with our rover and our autonomy folks about. Now, ice mining, there are several different concepts. I mentioned the beamed energy, driving off volatiles. People have talked about making solar tents or domes that heat up the surface. And then there's the the in situ kind of auger material and heating it up. And there has been work in all of these, microwaving processed materials to see about driving off. And in the case of this area, Honeybee has done 2 different approaches. The MISWE was initially done similar to this, and then now they've been looking at a, I think, PVEX? Yeah, where you do some of that down hole. So these are concepts where if the material's reasonably close to the surface, you might do something along those lines. For the deeper Rodriguez well or deeper ice sheets, this is the concept that's currently gaining a lot of attention. As Chris was showing, I think 1 meter or 2 meter scale type of augers have been built. The Marte definitely shows that you might be able to go down to 10 meters reasonably well. And here the idea is you're drilling through some kind of a glacier till or overburden that you don't really care about to get down to the ice sheet, and then you send a heat probe or something else down there. So it's a 2-step process. One is, what do I need to do to get through the glacier till to the ice sheet? And then the second is, once I've reached the ice sheet, how do I actually extract that material? So there are things that we could look at terrestrially from the Rodriguez well. And as Chris pointed out, there is a RASCO Mars Ice Challenge. They did it in 2017. No team really won, so they're redoing it again this year. I've been honored to be part of this year's activity, so I'm really looking forward to seeing that. And here's basically a concept of operation that might go along with that, where here maybe we have a multi-segment drill, maybe we have some other different technique that Chris was talking about, but basically, how do I get through that overburden? If it's all nice granular material, that would be great, but I just don't feel that that's going to be possible. So you may have to do some prospecting with a ground penetrating radar to not only look for the ice sheet, but to look for any obstructions to your drilling apparatus. You create your hole, you probably have to plug it up and pressurize down here so that you can maintain a liquid state. And as Chris pointed out, it takes a lot of thermal energy, but we may have a lot of thermal energy available with a nuclear reactor as long as we can learn how to tap into that. So we're looking at that particular concept. I'll just quickly mention the thing about planetary protection and ISRU. We're both very interested, or life detection and ISRU, we're very much both along the lines of follow the water. And so therefore, we are very much interested in a lot of the same instruments, at least to find and characterize that water before we do the search for life. And here are some different, concepts of instruments that we might fly. What hasn't been discussed about that really does need to take into consideration is planetary protection. And that is, we have to consider both the forward contamination of the hardware we bring if we're looking for water volatiles or life, as well as back contamination in the creation of potential special regions. With respect to ISRU and planetary protection, they're both the same. However, search for life, but when we start thinking about ISRU, we actually do now introduce several more contamination paths that we need to consider. If I'm bringing subsurface material up to the surface and an astronaut's nearby, now I have the possibility of not only contaminating the suit, but bringing that suit back into a pressurized habitat. So basically, we need to consider these things as we go forward. One of the things I haven't talked about at all is there's significant work going on in what's called biological or synthetic biological ISRU. That raises a whole other host of issues with respect to planetary protection rules for Mars that I purposely don't cover. Again, water summary. Basically, there are some things that because of planetary protection, we're not really considering. Somebody, I think, during the question and answer period talked about aquifers. We pretty much have been ignoring those in case there is some life issues, the slope lineae as well. But subsurface ice opens up some very interesting questions about planetary protection and the search for life. And basically, we do need to consider things about, with respect to the Rodriguez well, that we are creating a special region. So at this time, we don't believe that that would be allowed under current planetary protection rules. However, going after hydrated soils, we think we can operate under current planetary protection rules based on, sterilizing our hardware ahead of time and doing certain processes. And so in conclusion, with respect to that, we do think that we had proposed rules and guidelines with respect to ISRU for excavation and soil processing of granular and hydrated minerals. We do think we can do these things as long as we, do some cleaning and maybe even UV light while we're doing our operations. However, we do think that some rules will need to be changed, either through doing some sample analysis that shows that there's no life, doing some planetary protection rules changes that say, well, once we send humans there, we're going to be contaminating anyway, or some combination of those. And with that, I am done.